In the last segment, we talked about special types of double replacement. Once you figure out whether you have a precipitate, yes or no, you look for acids and bases, which will give you heat. If you create H2SO3 or H2CO3, you expect to see a gas. Okay? Segment 5 begins with other things that you expect to experience when you do reactions in the lab. One is combustion, which will feel warm to you, or other reactions that feel cool to you. Now, the idea of heat flow we'll come back to in Unit 5. Okay? All right, so for the combustion reactions, we want to go back to them and add heat. Okay, so let's find them in your notes. For example, on page 5, we don't want to forget that that's going to give off heat. And on page 4, we want, as a bit of a reminder, that all of these are going to give off heat. We're just temporarily ignoring them. Okay? All right. Now, for the moment, we're going to omit quantitating heat. It's kind of like your thermostat on your house. Is it 68 degrees or is it 78 degrees? Is it 58 degrees or is it 72 degrees? What is it? We're going to come back to that. Okay? Now, the other thing you want to be looking for is a new solid forming. And this is different than a precipitate, because a precipitate is an aqueous plus an aqueous yielding something that is insoluble. Okay? Now, this is the requirement to go back to the single replacement, which is also redox. But you have to ask yourself about the guy and the girl together and the new guy coming along, bumping the old guy off, so to speak. You should think about this suspiciously. The only time that's going to happen is if the new guy coming in is more wonderful, or the new girl coming in, however your point of view. Okay? Now, where you go look is an activity series. Okay, now there should be an activity series at the end of your notes. Okay, so this is most active or most wonderful. This is least. Okay, so for example, sodium will be able to displace gold, but gold will not be able to displace sodium. By the way, let's put lithium in there somewhere. Okay, so if we go back to the single replacement reactions that I showed you, where I assumed that they would all go forward, okay, page 3, is lithium higher than lead? Lithium is higher than lead, so yes, that one will go forward. Is magnesium more active than hydrogen? Well, yes, magnesium is more active than hydrogen. And when you check this chart, you will see that the only one that would not go forward is this one, because gold is definitely less active than lithium. So now that we know this, our assumption was wrong, and we would cross that out. Okay. Now, moving forward, we're going to talk about something that is reasonably new, okay? And that is something that we call a net ionic equation, and this does not appear very well in your textbook. Okay, so we talked about what it means to be soluble, okay? So soluble. If I have NaOH and it's solid, and I put it in some water, our solubility table tells us it's soluble, which means it is aqueous. Okay, so when we did our double replacement, we just did this, and we kind of ignored what that really looked like. But let's come back and let's talk about what that's really going to look like. Okay, What that will really look like is that we have a big thing of water, and we have sodium ions surrounded by water, hydroxide ions surrounded by water, and this will look like water to us. By the way, never drink anything like that. Okay, sodium hydroxide would be like Drano. Okay, so what we want to do is that if we have ions that are floating around in solution, we want to just cancel them out. Okay, so if we have, for example, NaCl plus NH4OH, we want to predict the products just like we did before. Okay, NaOH plus NH4Cl, and that would be our total molecular equation. We are treating everything as if it is a molecule. Okay, but the reality of it is we know that these are ions in solution because these are aqueous. Okay, so what we really have is Na plus floating around, chloride floating around, ammonium floating around, and hydroxide floating around. The question is, what does our solubility table tell us about the sodium hydroxide and the ammonium chloride? Well, it's going to tell us that these are aqueous as well, which means we have to break those up into ions as well, because that's the reality. They're just ions floating around in solution. All of these are aqueous, 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 aqueous. Okay, so this is all going to look like water, and this is all going to look like water. Then we want to go through and we want to figure out the net ionic equation by crossing out spectators. And spectators are what you see on both sides that haven't changed. So the sodium hasn't changed, so it's a spectator. The chloride hasn't changed, so it's a spectator. The ammonium hasn't changed, so it's a spectator. The hydroxide hasn't changed, so it's a spectator. And so the net ionic equation is that everything's a spectator, and what you just have is a solution in which you have a whole bunch of ions just floating around, and you have no net equation. Okay? All right. Let's try magnesium plus HNO3. Okay? Type of reaction will be single replacement. Single replacement means you always want to check the activity series to see if the reaction is actually going to go forward. MgNO3 2 plus H2, 2 here, this is a gas. Total ionic, this is solid, this is an acid, so we're going to separate that. Solubility table tells us this is soluble. Gas is a gas, which means we need to leave it intact. Spectators is only nitrate, which tells us at the end of the day that magnesium will be transformed into magnesium ion and hydrogen will be transformed into hydrogen gas. Okay, we will continue to work on more of these because this is new.